Welcome to our channel. Today we're diving into a fascinating topic. How does a planet's atmosphere, its life-giving shroud, disappear into the vacuum of space? It's a cosmic mystery that has puzzled scientists for centuries, and today, we're going to unravel it together. Imagine a planet vibrant and teeming with potential, slowly being stripped of its protective layer, its air and water scattering into the cosmos. This isn't science fiction, my friends. It's a very real phenomenon that has shaped the destiny of planets across our solar system and beyond. Over the next few minutes, we'll explore the forces at play, the consequences of this atmospheric exodus, and whether we can do anything to prevent it. So, buckle up, fellow explorers, and prepare to journey from the familiar to the far reaches of our cosmic neighborhood. Our universe is a dynamic, often chaotic place, and planets, despite their apparent permanence, are subject to a cosmic tug-of-war. One of the most significant threats to a planet's atmosphere is the relentless onslaught of solar wind. Picture a constant stream of charged particles spewing from the sun at supersonic speeds, bombarding planetary atmospheres like an invisible sandblaster. This solar wind, while essential for phenomena like the auroras, can strip away atmospheric particles over eons, especially if a planet lacks a protective magnetic field. Think of our own Earth, enveloped by a magnetic field generated by its molten core. This field acts as a shield, deflecting the brunt of the solar wind and safeguarding our atmosphere. But what about planets less fortunate? Mars, once a world with a thicker atmosphere and flowing water, serves as a stark reminder of the sun's erosive power. Over billions of years, the solar wind, unimpeded by a substantial magnetic field, stripped away much of Mars's atmosphere, leaving behind the desolate, thin-aired world we see today. Then, there's thermal escape, a process driven by the very energy of a star's light. When atmospheric gases absorb sunlight, their molecules become energized, moving faster and faster. If this energy isn't contained by a planet's gravity, these speedy molecules can reach escape velocity, essentially evaporating into space. Lighter molecules like hydrogen and helium, with their zippy nature, are more prone to this escape, which explains why Earth, with its stronger gravity, has held on to more of its nitrogen and oxygen. But for smaller planets with weaker gravitational pulls, thermal escape can be a death knell for their atmospheres. Let's not forget the dramatic, almost cataclysmic events that can reshape planets in the blink of a cosmic eye. Giant impacts. Imagine an asteroid, a rogue planet, or even a comet, hurtling through space at unimaginable speeds, only to collide with a planet in a fiery, explosive embrace. These collisions release unimaginable energy, capable of blasting significant portions of a planet's atmosphere into space. Imagine the early solar system, a chaotic billiards game of planetary formation, where such impacts were far more common. Evidence suggests that even Earth experienced such a cataclysm, leading to the formation of our moon. While these impacts are less frequent today, the threat, however small, still looms. And then there's gravity itself, the very force that holds planets together, which can also play a role in atmospheric loss. Smaller planets and moons, with their weaker gravitational pull, struggle to hold on to their atmospheres, especially against the relentless forces of solar wind and thermal escape. Think of it like a game of cosmic keep-away, with larger planets like Jupiter and Saturn, with their immense gravity, acting as bullies, pulling away the atmospheres of smaller, less massive bodies that stray too close. This gravitational thievery has likely shaped the evolution of countless celestial objects, leaving them as barren, airless husks. Finally, we have chemical reactions, a more subtle but equally impactful culprit in atmospheric escape. Certain chemical reactions in a planet's atmosphere can transform gases into heavier compounds, which are less likely to escape into space. Conversely, other reactions can release lighter gases, making them more susceptible to being whisked away by solar wind or thermal escape. The balance of these chemical reactions, influenced by factors like volcanic activity and the composition of a planet's surface, plays a crucial role in determining the long-term fate of its atmosphere. It's a delicate dance, a constant interplay between creation and destruction, with the very breath of a planet hanging in the balance. The consequences of atmospheric loss are profound, transforming a vibrant, potentially life-sustaining world into a desolate, unforgiving wasteland. One of the most immediate and obvious consequences is the loss of liquid water. Water, the lifeblood of our planet, relies on atmospheric pressure to exist in its liquid form. As atmospheric pressure dwindles, the boiling point of water decreases, leading to a phenomenon known as runaway evaporation. Lakes and oceans shrink, eventually disappearing entirely, leaving behind parched riverbeds and vast, arid deserts. Mars once again serves as a poignant example of this tragic transformation. Billions of years ago, Mars likely had a thicker atmosphere and abundant liquid water, perhaps even vast oceans. Today we see evidence of this watery past in the form of dry riverbeds, ancient lake basins, and minerals that form in the presence of water. But the liquid water itself is long gone, lost to the relentless forces of atmospheric escape. Without a substantial atmosphere to act as a blanket, a planet becomes susceptible to extreme temperature swings. On Earth, our atmosphere helps regulate temperatures, preventing drastic fluctuations between day and night. But on a world stripped of its atmospheric insulation, temperatures can soar during the day, only to plummet to frigid depths at night. Imagine baking under an intense sun, with no ozone layer to shield you from harmful ultraviolet radiation, and then enduring a bone-chilling freeze as darkness falls. This is the harsh reality for planets that have fallen victim to atmospheric loss. Their surfaces become scarred by extreme temperatures, hindering any chance of life as we know it from taking hold. Speaking of radiation, a planet's atmosphere plays a crucial role in filtering out harmful radiation from the sun and the cosmos. Our ozone layer, for example, absorbs most of the sun's ultraviolet radiation, protecting life on Earth from its damaging effects. But without a substantial atmosphere, a planet becomes vulnerable to this invisible bombardment, rendering its surface sterile and inhospitable. Imagine a world constantly bathed in harmful cosmic rays, with no protective shield to deflect their damaging energy. This radiation would wreak havoc on any life that managed to evolve, causing mutations, cancers, and ultimately, extinction. The lack of a protective atmosphere turns a planet into a sitting duck, exposed to the full fury of the cosmos. And of course, the most significant consequence for life as we know it is the loss of breathable air. Without an atmosphere to retain gases like oxygen, a planet becomes utterly uninhabitable for humans and most other life forms. We rely on our atmosphere not only to breathe but also to regulate temperature, pressure, and protect us from harmful radiation. Imagine stepping onto a planet devoid of air, your lungs struggling to grasp for a breath that never comes. The silence would be deafening, broken only by the sound of your own labored breathing, a stark reminder of the preciousness of our own atmosphere and the fragility of life in the universe. Chapter 3. A Second Chance. Can we restore a lost atmosphere? The idea of a planet losing its atmosphere might seem like a one-way street, a cosmic inevitability. But what if we could intervene, to protect existing atmospheres or even restore those that have been lost? It might sound like science fiction, but scientists are exploring several intriguing possibilities. One such concept involves creating artificial magnetic shields to deflect the solar wind. Remember how Earth's magnetic field protects our atmosphere from the sun's relentless barrage of charged particles? Scientists envision deploying large-scale magnetic fields in space, strategically positioned to deflect the solar wind and shield vulnerable planets. These artificial magnetospheres, as they're called, would act like giant umbrellas, providing a much-needed buffer against the sun's erosive power. Another approach focuses on manipulating a planet's greenhouse effect. Greenhouse gases, often demonized for their role in climate change on Earth, could actually be used to our advantage on other planets. By releasing carefully calculated amounts of greenhouse gases into a planet's atmosphere, we could potentially thicken it and warm the planet's surface. This process, known as terraforming, aims to make a planet more Earth-like, potentially habitable for humans and other life forms. Imagine transforming a cold, barren world into a temperate oasis, with flowing water and breathable air, all thanks to the strategic manipulation of greenhouse gases. And then there's the audacious idea of cometary bombardment, a concept straight out of science fiction. Comets, those icy wanderers of the cosmos, contain vast amounts of water, ice, and other volatiles. Scientists envision carefully redirecting comets to collide with planets, delivering a payload of water and other essential ingredients for life. These controlled impacts would release their contents into the planet's atmosphere, potentially thickening it, and even jump-starting the formation of oceans. It's a bold, ambitious plan, fraught with challenges, but the potential rewards are immense. Imagine breathing life into a dead world, transforming it from a barren wasteland into a vibrant, water-rich planet, all thanks to the strategic bombardment of comets. These are just a few of the ideas being explored, a testament to human ingenuity and our desire to extend life beyond Earth. While these concepts are still in their infancy, They offer a glimmer of hope, a reminder that even in the face of cosmic adversity, we might find ways to protect and even restore the delicate balance of life-sustaining atmospheres. Remember, we are a species with a remarkable track record of overcoming seemingly insurmountable challenges. From splitting the atom to landing on the moon, we have consistently pushed the boundaries of what's possible. The quest to understand, protect, and even restore planetary atmospheres is just the latest chapter in our ongoing exploration of the cosmos. Who knows what incredible discoveries and technological marvels await us as we delve deeper into the mysteries of the universe. The future of planetary exploration is bright, and the possibilities are as limitless as the cosmos itself. Thanks for watching. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more fascinating content. As we've explored today, the fate of planetary atmospheres is a tale of cosmic forces, delicate balances, and the potential for both destruction and renewal. Understanding these processes not only deepens our appreciation for the preciousness of our own planet, but also fuels our imagination as we look to the stars. See you next time.